Hello Chemistry, here we are starting chapter 15 section 1, and a very familiar location for a lot of you. Stopped here on your way into class to get a little drink of water. Now, when you were drinking the water, were you drinking an acid or a base? Was it neutral? Or is it both? What were you drinking? What's in that water? Let's take a look. That cool, clear water was really good. Got a good drink here before we take any steps farther. Yes, we're starting chapter 15, acid, base, titration, and pH. Quite a journey to go through here. And yes, this chapter is going to involve a little bit of math. So fasten your seatbelts because you're going to get a little answer to when am I ever going to need to know this when it comes to math. So, water. Well, water does some very interesting things. And I'm going to write one of the strangest equations that you probably have seen me write. We're going to write a reaction of water plus water. And what do you think we can get when you add water plus water? Now, normally I would expect just to get water. But what can happen is one of them can give a hydrogen, a proton, to the other one. And so we can get something really strange. We can get hydronium ion. Now if he gives us hydrogen and this becomes hydronium, what does the other guy become? Hydroxide ion. But we would get equal amounts of both of them. And this has a name. This is called the self-ionization of water. And you can see it right here in your book. Talked about the self-ionization of water. I'm not making this up. Water plus water equals the hydronium ion plus the hydroxide ion. And it turns out that using conductivity, like putting a light bulb into water, we can figure out about what the concentration is, and that's around 1 times 10 to the negative 7 moles per liter at 25 degrees, which is about room temperature. Here's a diagram at the bottom of your page showing you a water molecule. Another water molecule yields the hydronium ion, that's the oxygen with 3 hydrogens, and the OH, hydroxide ion. All right, if you flip the page, you will see on page 480 that we're going to talk about the ionization constant of water. But before we talk about that, we need to talk about some notation. You know, in chemistry, we have subscripts, superscripts, and all kinds of little symbols to help us understand what things mean. Well, we're going to get to learn a couple more here, and that is we're going to put brackets around substances that we want to show the concentration of. Instead of saying a long thing that says hydronium ion concentration in moles per liter, we can just write this right here. Brackets, H3O plus, and brackets, and that means exactly the same thing as saying hydronium ion concentration in moles per liter, or molar hydronium ion concentration. That's a mouthful, so it's much easier even writing to do this. Now, for water, it turns out because we're going to break, just when we break these apart, we're going to get just as many of the hydronium as we do of the hydroxide. And if our concentration is, remember this is saying the concentration of, is 1 times 10 to the negative 7 of hydronium ion concentration, then it must be the same number for the hydroxide ion concentration. Now, is this a big number or a small number? Remember that 1 times 10 to the negative 7, why did I write a 3? A 7 is the same as writing 0.1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That is that number. It's an extremely small number. So we're not talking about a very big thing. So when you're out there drinking at the drinking fountain, you're getting this many hydronium ion ions, and you're getting this concentration of hydroxide ion concentrations, which would easily go back to this and form water. So there's no big danger, no danger at all in drinking water as far as the acidity is concerned or the basicity. Now, we're going to put this into a constant, and this K stands for a constant. The W is representing water, and we take the two things here, which we read as hydronium ion concentration and hydroxide ion concentration, and we're going to multiply those two numbers together. Well, in plain old water, those numbers turn out to be the same. And when you multiply them together, you get 1 times 10 to the negative 14, which is an extremely small number. Remember what we do with exponents. This is going to become relevant coming up here, and that is that a negative 7 and a negative 7 equal a negative 14. Remember what we do with exponents? For example, if you had x squared times x to the 5th, what would be the answer to that? That would be x to the 7th, because the exponents add. Same thing happens here. Now, ionization of water changes. It can increase as the temperature increases or decrease as it decreases. And you can see in the chart here, at 0 degrees, there's a lot less ionized water. And at 50 degrees, there's a lot more. Still a very small number, but there's more. Remember we talked about way back dissociation and ionization. This is called the ionization of water. Why? Because beforehand, this was a covalently bonded substance, and now it's becoming an ionic substance and forming ions. So that's why it's called the self-ionization of water. Now, if we have equal concentrations of both, like as we do up here, then we're going to call that neutral. However, if, as we learned with Arrhenius acids, if we have more hydronium than hydroxide, we're going to say that it is acidic. If we have more hydroxide ion than hydronium ion, then we're going to say it is basic. So things that increase hydronium are acidic, and things that increase hydroxide are basic solutions. So now let's take a look at some of the math that goes along with this. Strong acids and bases completely ionized. This is important because let's say that we're mixing some sodium hydroxide with some water, and it's going to, in this case, dissociate because this is already ionic. This is a dissociation. And however many moles of this we have is how many moles of each of these we're going to have. When it comes to acids and bases, we don't really care about this guy. We only care about the hydroxide ion concentration. Well, this mathematically makes it easy because it's a 1-to-1 ratio. Nevertheless, we still are good to show our math because it won't always be a 1-to-1 ratio. So if we have 1 times 10 to the negative 2 concentration of sodium hydroxide, the mole ratio is 1-to-1, and we're going to get the concentration of the hydroxide ion, which in your homework you're going to start getting lazy, and you're just going to say, whatever that is, that's what this must be. But it takes it one step further. Well, what is the concentration of the hydronium ion? Hydronium ion. Well, we can do a little math, and we can say, all right, we know that Kw equals 1.0 times 10 to the negative 14. We also know that that equals the hydronium ion concentration times the hydroxide ion concentration. Well, we can separate, we can put in for those numbers the concentration, and in this case, we don't know the hydronium ion concentration, but we do know the hydroxide ion concentration is 1 times 10 to the negative 2. 1 times 10 to the negative 2. So we know that that overall has to equal the ionization constant at room temperature of 25 degrees. So just like good old algebra, pretend like this is a giant X. How do we get it by itself? Well, we divide by this concentration over here. That cancels. What I do to one side, I must do to the other side. And then you grab your handy-dandy calculator and you put these numbers in there. Just a reminder, when you do this, you've got to use this button on this calculator or the EE button on the TI. So we're going to go 1, then I'll push this button. I got to remember to push this negative. Don't push that one, push this one. 14, and we're going to divide by 1 to the negative 2. And we get that 1 times 10 to the negative 12 12 is the concentration of the hydronium ion. Now this is extremely small compared to the hydroxide ion concentration. So what kind of solution is this? This is very basic because this is much smaller than that -7 and this is much bigger. Even though it's still small, it's much bigger. We can do the same thing with another compound that might be acidic, and your book goes on and gives this example of hydrochloric acid. Again, when hydrochloric acid breaks apart, it breaks apart as a 1-to-1 ratio. So just like we did up here, the mole ratio is a 1-to-1. We get the same concentration for hydronium ion as we do the hydrochloric acid because it is a strong acid or a strong base. If it was weak, why we don't know this 1-to-1 business. So we're going to start out with the easy stuff, the one that completely forms ions. So we do the same kind of math here where we say 1 times 10 to the -14 equals the concentration of both. We divide by the concentration of the hydronium ion and you get an answer. Now this one was a little more tricky because the math on this is super easy. All you have to do when you divide by exponents, like if you had x to the 5th divided by x to the 2nd, what's your answer? Well, that's x to the 3rd, because we could have x times x times x over, that's the same as that. Those x's cancel, and what are we left with? X to the 3rd. So what do exponents do when you divide? They subtract. 5 minus 2 is 3. We can do the same thing here. 14 minus a minus 2. So when you subtract a negative, you have to add it, right? So what's 14 plus 2? It's -12. Well, that's always nice and easy there. We don't even need to use our calculator. Here, it gets just a little more tricky. Now, there's some of you that can do it in your head just fine. But notice when there's a 2 in front, we can't just get lazy and subtract our exponents because 14 minus a minus 4 should be 10. But what is 1 divided by 2? It's 0.5. And so you have to move the decimal one more place over, and that becomes -11. I bet your calculator will tell you that as well. Another way to think about this ionization constant is that this is, in fact, constant. So the only changes that can happen are over here. So if we increase the hydronium ion concentration, we make it more acidic, what has to happen to the hydroxide ion? It has to go down. So this is an inverse relationship, and it kind of makes sense because if we increase the number of these guys, they're going to want to, more of them, join with the hydroxide ions that are there and take them out of circulation so that we form more water. So that's going to reduce the number of these guys and increase the concentration of these guys. Now, with this constant, you have an example in your book of some problems to do here. And here we have a concentration of nitric acid. And we want to calculate the hydronium ion concentration. Well, that part's pretty easy because they show the big fancy calculation, which is correct. Since it's a strong acid, it's going to completely form ions, and that concentration will be the same as the hydronium ion concentration. Since it only has one hydrogen that it can release, the mole ratio is 1-to-1, and so that number will be the same as the number that was given in the first place. So that's really super easy. And the hydroxide ion concentration, again, you just take the 1 times 10 to the -14, divide it by that. Since they're both 1, we can just go -14 minus a -4, and that becomes 10. The thing I want to point out to you to watch out for is, what if you have something like calcium hydroxide and there's a 2OH? Well, you're going to have to pay attention, and whatever your calculation is here, you're going to have to do a mole ratio of 2-to-1. And that's going to double that. So whatever the concentration is over here, so if it's 1 times 10 to the -4, when it forms ions, it's going to be 2 times 10 to the -4. Now, some of you are lazy, but you're a smart lazy. You say, you know what, this still is a lot of work. Even though we're writing concentration here, when we're writing 1 times 10 to the -14, is there even an easier way to write this? So we notice that if I wrote it this way, 1 times 10 to the negative 7, you know, just like what we did up here, 2 plus 5 is 7. I can almost ignore all that because I know that that's what's the base. So what we can actually do here is we can say, I'm so lazy, I'm going to, instead of negative 7, I'm going to just write 7 plus 7 is going to equal 14. Now, it was negative here, and it would be all negative, but I want to be even lazier than that. We always know we're talking about chemistry and the concentration, so to be really lazy, we're going to say, well, that 7 plus that 7 would equal 14. We're just basically adding exponents and dropping off the base for those exponents. Well, the fancy term for taking the exponent and just making it into a number is called using the log of the number. So let's kind of review here a little bit of how this thing works. Let's say that we have some hydrochloric acid, and we want to know what the concentration is. We can take that concentration, and we know that since it's a strong acid, whatever its concentration is, that will equal the hydronium ion concentration. Well, how could I figure out the hydroxide ion concentration if I know the hydronium ion concentration? Well, to get from here to here, you would just simply take that ionization constant of water, which is Kw. That should be a little w, Kw. And we're going to divide it by whatever that concentration is. So to get from here to here, that's what I would do. Well, what would I do if I got, say, some sodium hydroxide? If I know the concentration of that, since it's as strong as a base and it completely forms ions, that concentration will be the same as this one. What if I want to know the hydronium ion concentration then? What do I got to do? Well, again, I take that same constant and I divide it by the concentration of the hydroxide ion. That's how I go from here to there. But you say, oh, I'm so lazy. This is a lot of numbers to write. How about we just go with the exponent? Well, we can go to what we call pH. I shouldn't write a bracket here. We're just going to write pH. All right. pH stands for the power of hydrogen. pH. Now, when it comes to writing it, don't embarrass yourself or anybody else by writing. Don't write pH. That's bad. Don't write pH. That's bad. Don't embarrass yourself. Write it always the correct way. There's the right way, and it stands for the power of hydrogen. Well, the power of hydrogen is our lazy way of saying 1 times 10 to the whatever. And if I want to know what this one is, how do I go from here to here? Well, I just do the log of whatever that concentration is. So let's say the concentration is, is 1 exponent to the negative 2. That's the concentration of the hydronium ion. 1 times 10 to the negative 2. What would be the pH? Well, I can just simply push log. Actually, I need to push log first. I go 1 to the negative 2, and it will give me the log of it. Well, we already talked about I want to be lazy and not use that negative. I can just say 2 because we know what we're talking about. So let's let's make this negative to start with. So let's start over with that, and let's go negative log 1 times 10 to the negative 2, and you get, oh, how beautiful is that? Plain old 2. So that would be the pH. Well, what if I know the pH and I have to, somebody's asking me for what the concentration was? How do I get there? Well, on your calculator, you're going to do anti-log of the negative pH. Why do we have to do negative? Well, because we lost it coming this way. We got to put it back going this way. So let's say that I know my pH is 2, and I want to go back this way. So I'm going to go, I have to use this same button. Do not get tempted to use this button or any other button that's on here. There's other ones that are tempting. So I'm going to go Shift, and I'm going to go anti-log. I got to put a negative 2 in here, and there I get 0.01. And a lot of students say, oh no, that doesn't look like anything I know. Well, how would I write 0.1 in scientific notation? Well, 0.01 is the same as writing 1 times 10 to the negative 2. Oh, there's the concentration of the hydronium ion. And we're back to where we came from. So that's the pH. Well, what if I wanted to know the hydroxide ion concentration? Well, that also has a name, and that's pOH. Well, if pH stands for power of hydrogen, what do you suppose pOH stands for? It's the power of hydroxide. So how would I get from here to here? Let's say that our pH is 2. How would I get to over here? Well, we already know that when it comes to exponents, we just subtract. So I would just go 14 minus 2, or if I'm not just doing any particular number, I'd go 14 minus the pH, and over here I am. So in this case, it would be 14 minus 2. What would be my pH, pOH? It would be 12. And what if I knew my pH, pOH, and I wanted to go this way? I would just take 14 minus the pOH. So 14 minus 12 would be 2. You're starting to get the idea of how we can go around this chart. Now, if I had 1 times 10 to the negative 2, how would I find the concentration of hydroxide over here? Remember, I would take this number divided by that number. So in this example case, that would get us to be 14 minus the minus 2 would be 1 times 10 to the negative 12. Well, how could I go from here straight to here? Well, I would do the same thing like over here. I would go negative log of the concentration of the hydroxide ion. Let's just do that for fun on the calculator. So I'm going to put in here and I'm going to put a negative in front, negative log the concentration 1 exponent to the negative 12, and what do we get? Oh, look at that, a 12. That's the pOH of this hydrochloric acid that came into here. And you can probably see where this is going. What if I wanted to go back up this way? I again would do the anti-log of the negative pOH. So let's just take that number we just got and let's go anti-log. So I'm going to push this shift button to get that little red or orange colored thing up there. Anti-log of, I got to get that negative back, so I'm going to put a negative 12, and the calculator returns for me 1 times 10 to the negative 12. Huh, that's where we were. So you will see that I've made for you one of these charts, and you have it in your handout. So this is where you would take whatever substance you have coming in. Notice it says monoprotic, because if it was diprotic or triprotic, it could mean that we have more of those. And same thing here. Hydroxide, if we have sodium hydroxide, we just have to watch out for something like calcium hydroxide, which would put out 2 of these for every one. You just have to double it by the time you go into here. So here on page 483 is where we talk about what I just showed you on this drawing right here, of how we get our pH and pOH. We just simply take the negative log of whichever concentration we have. And as we talked about, because it's just exponents, if they're together, they must add up to be 14. Well, pure water has the same concentration of hydronium and hydroxide ion concentration. So here it shows you just one scale. This is the hydronium ion concentration. When it is 7, -7, what's the pH? It is 7. We just take that negative exponent. Now, as we get more and more hydronium ion concentration, we're getting more acidic. Our pH actually goes down because our exponents are getting smaller and smaller as our number gets bigger and bigger. By the same token, if we get less and less hydronium ion concentration, it gets smaller and smaller, and so we say that it is getting more and more basic, because when one of them goes down, the other one must go up to maintain that same number. So we talk about this being the pH scale. You'll notice that there is no pOH scale, because really, if we're talking about, let's say we have a pH of 3, do I know what my pOH is? Oh, it must be 14 minus 3. Oh, it's 11. So we don't even talk about a pOH scale, because if we know one, we really know what the other one is. The rest of our section basically goes through all the calculations, or way to do the calculations, that we just talked about on this paper here. But there are a few more things that we need to touch on that are in the remaining part of this section. One of them is this table. This table talks about what the pH would be of different substances. Notice that we've right away slipped into no longer talking about concentration in terms of something 1 times 10 to the negative whatever. We now are just talking about it in these logarithmic numbers. So it gives you some common substances and their pH. And if the pH is smaller than 7, we say it's acidic. If it is greater than 7, we say it is basic. Of course, because water is in the middle and it's neutral, it's at 7. And this is all happening at 25 degrees Celsius. As I said, the remaining pages mostly focus on the calculations that we just talked about and how to do the log and anti-log and so forth. In this section, it talks about, well, what about weak acids? Because what we talked about, we assumed in our diagram here that this guy completely ionizes and forms ions, or this guy completely dissociates and forms all of its ions. But what if whatever we put in here doesn't do all that? How do we know how much it's going to make? The answer is we have to do it experimentally. So for weak acids, weak bases, you cannot calculate it directly. We have to do it experimentally. We have to do some experiments. And that is what we're going to talk about in the next section. There's one more thing that you need to know. And there's probably going to be a collective groan as I tell you, we have to talk about significant figures. So in your book, it talks about, when we go to logarithmic numbers, that there must be as many significant figures to the right of the decimal as there are in the number whose logarithm was found. Oh boy, so what does that mean? Well, what if we had 1.0 times 10 to the negative 8? What would be the log of that number? Well, the log of it would equal 8, because the negative log, I should say, would equal 8. But what does that number tell you? It tells you that if we were to write that number, we would have moved it over 1, 2, 3, 4, 5, 6, 7, 8 decimal places. So this number tells you how many decimal places we move the decimal. Does that tell you how precise the number is? And the answer is no. That's just how many decimal places. So this number is telling us the number of decimal places. It does not tell us the number of significant figures. So if we have here 2 sig figs, 1, 2, we need to answer with 2, and the 8 doesn't get to count. So the correct way to write it with 2 sig figs would be 8.00. That's going to bother a lot of you, but here are our 2 sig figs. This does not count as a sig fig or significant figure. So lots of times you'll see a number written 1 times 10 to the negative 8. How would I write that in logarithmic number? I would write 8.0 because here is 1 sig fig. And over here would be 1 significant figure. So if we have 1.0 times 10 to the negative 8, I would write 8.00. And then I get, here's 2 sig figs. And here are the 2 significant figures. So you got to watch out for that going back and forth. And it can even be more tricky because what if we have 1 times 10 to the negative 12th? Well, how would I write that as a negative log? That would become 12. But this tells me how many decimal places to move it. That is not 2 significant figures. Here I have 1, so I need 1 over here, so I'm going to have to write 12.0 significant figures. By the same token, if I have something like 11.00 and I'm going this way, I would have to write 1.0 times 10 to the negative 11. Here are 2 sig figs. I know it bothers you. There's 2 zeros that are significant figure. The 11 is not. And here are 2 significant figures. Finally, I would like you to just write a reminder on your homework here. I want you to write S.F or, S.F would be fine. And that is to remind you to put on there sig figs, okay? Let's just look at one quick example here in your homework. Calculate the following values without using a calculator. In other words, try to do it in your head. Usually I ask you to show your work and everything, but in this case, we can be lazy. So if we know the hydronium ion concentration is 1 times 10 to the negative 6th, what would be the OH? Well, we would just take the 1 times 10 to the negative 6th, and you know it's going to get, divided by 1 times 10 to the negative 14, what exponents do. So you got 14 minus a minus 6, so you get negative 8. So our final answer is going to be for letter A, 1 times 10 to the negative 8. That's for A. So here you get to watch out for the number of significant figures. Here you shall, if it's because pH, there's only 1 sig fig. Here there are 2 significant figures. And this is where you're going to need to use your calculator. Here you can do it without a calculator pretty easily. Here it gets a little harder, and you may need to use a calculator. All right, that's it for now, and please come visit me on the video if you have questions.